Hi, this is Professor Fernandez, and this is video 4 in lesson 5. We'll be talking about continuity on an interval here, and we'll be doing that by examining examples that give us the actual formula for the function. So these examples are from Calculus Simplified, so let's take a look at the first one here. First one says, on what interval or intervals is f of x equals square root of x plus 1 continuous? Okay, so you could answer this question by looking at every single point in the domain of the function and then figuring out if it's continuous at that point. That would take a very long time, right? There are an infinite number of such points. So instead, we're going to appeal to these two theorems. So let me just zoom in to show you what they say. First one says, the following families of functions are all continuous at all points in their domain. So polynomials, power, and rational. Long story short, if you know that you're looking at one of these three types of functions, and you know what their domain is, they're automatically continuous for all those x values. So that's great. The second theorem says, well, how about if you're looking at a function that's not quite one of these three families, right? Maybe it's some combination of those three. Well, so this theorem says, suppose they're continuous, f and g are continuous at some point c. Then the sum is continuous at c. So is the difference. So is the product, right? And so is the function multiplied by some number. And so is the quotient provided we're not equal to 0 in the denominator. So that's a quick little rundown of what this theorem says. So let's look at these examples again, see if we can use any one of these theorems to help us out. So the first one here, we look at this and we're asking ourselves, first of all, is this function a rational function, a power function, or a polynomial? The answer is it's not any of those, right? Rational, remember, is polynomial divided by polynomial. Power function looks like x to the r, where r is a real number. And a polynomial looks like, for example, this is a polynomial. So this function that we're looking at, f of x, is not any one of these three. So we can't use this theorem, okay? So we're going to use this theorem. Can we now view this function as a sum, difference, multiple, product, or quotient of two functions that we know something about continuity for? And the answer is yes, right? So if we zoom in here, this is a power function, x to the 1/2. This is a constant polynomial, right? So y equals 1. So let's call these functions g of x, and let's call the other one h of x. Okay, so now we can go back and use our theorems. So this is great, right? So we have found that inside this f of x function are a power function and also a polynomial. So now this first theorem kicks in and says, oh, great. So if we can find out the domain of these functions, then the functions are continuous at all points in that domain. Great. So what is the domain of this power function? Okay, well, the domain of square root of x, I have to think about which numbers I can substitute in for x, and nothing goes wrong mathematically. And the answer is x bigger than or equal to 0. Okay. If I plug in any negative number, then I'm going to get square root of like -1, for example. That is not a number in this calculus class, right? It is what's called a complex number. You study that in future follow-up math courses. But for us, it has to be, the x value you plug in has to be non-negative, bigger than or equal to 0. Okay, what about for the polynomial? So h of x equals 1. It's the constant function, right? So if you were to graph this, it looks like that. So you can literally plug in whatever number you want. So the domain here is all real numbers. Okay, so this theorem, theorem 2.1, kicks in then and tells us that this function, h of x equals 1, is continuous for every single x value you can imagine. And this function, square root of x, is continuous for every non-negative x value. Okay, so that's a lot of information, because when we go back to the original function f of x and ask the original question, where is it continuous, we now have the answer. I can't even look at negative x values because the function is not defined there, right? For example, if I tried f of -1, it would be square root of -1 plus 1, right? That's not a real number. So first of all, the domain of this function, so domain of f of x is x bigger than or equal to 0. Okay, that just happens to be exactly the set where square root of x is continuous. We just figured that out. And also, it is part of the set where h of x equals 1 is continuous. So therefore, my theorem 2.2 kicks in. Because f and g, in this case, square root of x and 1, are both continuous at every point in this domain, then the sum is also continuous at every point in this domain. All right, so to remove the clutter and put down our final answer, we have just determined that this f of x function is continuous on this domain, right? Non-negative x values. So I'll just, oops, excuse me, I will just put that over here and box it as our answer. Great. So we're going to do this all over again for the second example here. This is a different function. So again, we have to go back to the drawing board and see which one of these theorems apply. First of all, is it a polynomial, power, or rational? In this case, we're a little luckier because it is one of these. It's a rational function, right? X is a polynomial, this is a quadratic polynomial, and a ratio, a quotient of polynomials is exactly what a rational function is. Perfect. So we can now use just this theorem. And this theorem tells us as long as I know what the domain is, right, then the function is continuous at all points in that domain. Great. So I now am looking for the domain of this function. Well, so that's the set of all x values that I can substitute, and nothing goes wrong mathematically. So I'm going to look at the denominator. The only thing really that can go wrong with a rational function is that you divide by 0. Okay, so I don't want to divide by 0. So I want to set this equal to 0 and then solve. Those will give me the x values that make the denominator equal to 0. I then have to exclude those from the real line to look at the domain, or to get the domain for g of x. All right, so now we're back to factoring. Okay, we did some of this in the earlier videos in this series. Lots of different ways you can do this, but eventually we factor this into x plus 2 times x plus 3. And just as a quick double check, this would be x squared plus 3x plus 2x, so that's 5x, there we go, plus 6, so that's that one. So all of that works out. Great, so now we're back to solving over here, and I get x equals -2 and x equals -3. Okay, at those x values, the denominator is 0. So the domain of g of x is everything up to -3, not including -3. Also everything between -3 and -2, not including -2. Also everything from -2 to infinity. Great. So I have a real line basically that's segmented into 3. So I exclude here and I exclude here, and then everything else in between is the domain. And because I am now, again, using this theorem and have found that to be the domain, then this tells me that this rational function is continuous at all points in that domain, right? So my boxed answer is this one. At what points on what intervals is a function continuous? There we go. Those are the 3 intervals, right? So that's a lot of points of continuity. Okay, so zooming out and just recapping, you can see the real benefit of these 2 theorems. Look how fast we were able to determine the intervals of continuity. We did not have to look at a bunch of different points and do this point by point, continuity at a point. All we had to do really was find the domains, right? This is a question about domain, and this is a question about continuity, which is kind of a question also about domain embedded in there. Great, so that was these 2 examples, and I'll see you in the next video.